a great weekend. I really enjoyed all the talks I got to see. So I'm going to be talking about some matrix factorizations of discriminants. And really, the motivation for these particular matrix factorizations I'm going to talk about are related to non-commutative resolution. So I'll write that down right as well. The non-commutative, so the point for me is that we get non-commutative resolutions out of these. And that's why I'm interested in them. But anyway, okay, let me just start off defining the first few things, the first few words here. So I'll start with discriminants. And we all know what discriminants are. But you know, the word, like a lot of words in math, it takes on a few different meanings. And so by the discriminant, I mean the discriminant of a polynomial. So if we had something like, you know, a t squared plus bt plus c, then we know the discriminant is b squared minus 4ac. That's our discriminant. Okay, so we're going to make life a little simpler. We're going to set a to be 1. There's not much point in having that there. And we're usually going to set the b to be 0 as well. Okay, so this discriminant is going to be very simple, and there's not a whole lot going on in this particular example, but there are higher degree discriminants that are going to be quite interesting. And so, but just to remind you, the point here is that the discriminant tells us when a polynomial has multiple roots. Okay, so what we're going to do is we're going to have the space of roots of polynomials. Okay, and I'm using t as my variable because I want to use x as the roots. So I'm going to have roots of polynomials, x1, xn. These are going to map to a polynomial. So these are going to be my roots. They're going to map to the polynomial t plus x1. And, well, we can write minus it. Well, maybe I should write minus. So I'm calling it really won't matter much if I write minus or plus here. Okay. Oh yeah, I'm going to write plus. It just makes the next step easier, right? So this is, everybody knows, it's t to the n plus the elementary, or some people use e here. I'm going to use that's a sigma 1 t n minus 1 plus plus sigma n. I'm going to use sigma for the elementary symmetric function. Some people use e's, but I'll stick with the sigmas. So we're going to have this map here. I'll call this map P for projection. And we're also going to impose that usually that the sum of the xi's are 0. So in other words, sigma 1 is 0. Just let's make life a little simpler. All right, so let's just take a look at the cubic discriminant first. Okay, so if we have a cubic, we have two variables kind of left over once I impose this condition. And they are x1 minus x2 is one of the variables, and x2 minus x3. Those are the two generators. And I'm drawing this other line here, the x1 minus x3. And these, we have an S3 action on this. And these are the reflection hyperplanes. These lines that I've drawn here are the reflection hyperplanes. All right. So this is happening in our space of roots, right? And then we can map to our space of polynomials. Okay, and so we're going to do a picture like this, and it's going to look like a cuspidal cubic. And at the level, this is happening sort of geometrically, but the level of rings, I'm going to have S is, say, K, x1, x2, x3, modulo the sum of the roots are 0. And then I'm going to have, say, an injection here. R is going to be S fixed by S3, they're the fixed ring. And we all know that's K adjoin sigma, well, I can write sigma 1, sigma 2, sigma 3. But of course, we're killing sigma 1. And that's all well known. And so the cuspidal cubic I drew there, this is the discriminant, and that's the image. So delta for discriminant is going to be minus 4 sigma 2 cubed minus 27 sigma 3 squared, and this is the discriminant. Okay, and it's the image of these 3 lines, right? So the 3 lines are where 2 roots, like a pair of roots coincide. So that's where we have double roots. And so it maps down to this discriminant here. And in fact, we actually have a formula. This is also equal to x1 minus x2 squared, x2 minus x3 squared, and x1 minus x3 squared. Okay, so there's a direct relation in terms of these relations. And this just follows, well, this follows from many things. All right, so that's basically what I want to say about just to introduce discriminants in a very simple way. And of course, we have higher dimensional versions of this for we'll have an S4 action on 3-dimensional space, and we'll have reflection hyperplanes and a very similar kind of picture there. So there'll be a hypersurface in 3-dimensional space cut out, but there'll be the discriminant of a quartic and so on. Okay, so it's harder to draw, but that's what we mean by the discriminant. It's just the basic discriminant of a polynomial. All right, so the next thing I want to get to is a matrix factorization. And so I am temporarily, I'm going to use power sum for a second here. Okay, so we also have P, so stick with S3 here, and I want to get to a matrix factorization. So I'm going to let Pi be x1 to the I plus x2 to the I plus x3 to the I. These are the power sums. And these, these are another set of generators for forms generators for symmetric functions. Newton's identities relates them to the elementary symmetric functions and so on. And now if I use the power sums, so this thing here, I was going to call this map here P for projection. And if I take the, I want to take the Jacobian of the map P. Okay, so, and the Jacobian, and I'm going to use the power sums as my variables. Okay, so when I write Jacobian, and so yeah, I know I just set sigma 1 equals 0, but I'm going to temporarily bring it back. So let's, well, we're going to bring back sigma 1 P1, just temporarily. Okay, it just makes the next calculation look a little nicer. All right, so that in that case, when we do that, the Jacobian of the map P is going to be, well, let me write it, let me make a little space here. It's going to be 1, 1, 1, x1, x2, x3, x1 squared, x2 squared, x3 squared. Okay, so that's going to be the derivative of the pi's with respect to the xi's, or maybe the transpose, but it won't really matter because I'm going to have the transpose over here. So depending on how you think about it, one is the Jacobian and the other is the transpose. Oops, x3 squared. Right, so we have those 2 matrices, and their product is 1 P1 P1, 2 P2 P2, P3 P3,
It's
and
a
P3.
3. 3, P1, P2.
Oh yeah, there's numbers there. Yeah, yeah. I really should scale everything if I want it to. Yeah. Do you mind if I'm off by scalars? I think that might just
No,
make life a little easier.
it's the
Yeah.
top left entry is a 3. 1 plus 1 plus 1 is 3.
Ah, is 3. Okay. Yeah. Yeah. You're absolutely right. Yeah. 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 And then of course, yeah. I mean, I'm going to be off by scalars a bit in this introduction here. That's true. That's definitely a 3. And then these derivatives I don't really write either unless I scale them. I scale the PIs. So maybe I have to put a 1 over I here or something to make it match. But yeah, yeah, but thanks for that, Francois. But I may get be off by a scalar here and there. Right. So this is the Jacobian. So depending on how you write your I's and J's here, one of these is the Jacobian, and the other is Jacobian transpose, and we're getting this matrix here. Okay, so the reason I wanted to bring up this matrix is it's part of a matrix factorization. So that's the discriminants I just was talking about. I want to talk about matrix factorizations now. And so the point now is that we know the Jacobian of T this is van der Maan matrix. Okay, and so we know the determinant of Jacobian transpose is going to be the same as this. And we know the determinant of van der Maan matrix is x1 minus x2, x1 minus x3, x2 minus x3. And of course, we're squaring all of these because we have the same determinant twice. Okay, and so that's going to be the determinant of this guy here. So if we take the determinant of this matrix, we get the same thing clearly. Okay, and so this is my discriminant delta, right? And so what's interesting now is let's maybe call this guy A here. A is going to form a half of what we call what's a matrix factorization. Okay, so if we let B be the determinant of A times A inverse, or sort of the classical adjoint. So this is the thing we do to compute the inverse without dividing by the determinant, right? So this will be in our ring. This B, the pair of A and B, are going to be a matrix factorization. Right here, maybe BA. Of delta. Okay, what is the definition now? So definition. So matrix factorization is a pair, say BA, of maps on a polynomial ring. So S is our polynomial ring. Oh, but I guess sorry, these are over R, the invariant rings. These are over the invariant ring. So I'm using R here. I mean, the definition won't matter. R is a polynomial ring. Okay, BA square matrices such that BA I have to say, sorry, let me do this right, this is a matrix factorization of delta if AB is delta times the identity and AB and BA are both delta times the identity. Okay, so that's the difference, the definition of a matrix factorization. So we're taking a function, a regular ring element, and we're multiplying it by an identity matrix so it becomes larger, and then we're factoring that as a matrix. So we're getting a factorization as a matrix. So it's certainly a delta is going to be irreducible, but that doesn't mean it won't factor as a matrix non-trivially. Okay. And so what I want to impress a little bit about why we might care about matrix factorizations. And so first off, matrix factorizations of delta. This is a category. And it has a direct summand, where the direct summand is the kind of obvious thing where you just take blocks of the matrices, and the morphisms are the kind of obvious thing too. So that's why I wrote that sequence there. We would have a sort of a map of those two sequences, and that's how you would define the homomorphisms. Okay, so one of the reasons matrix factorizations are important is the following theorem of Eisenbud. So matrix factorizations of delta. Delta doesn't have to be the discriminant, just any function, where we're going to mod out by the category generated by morphisms that factor through this. So it's like a stable category. So we're going to mod out by 1 comma f. This is kind of a trivial matrix factorization. We're factorizing f into two 1 by 1 matrices, and one of them is the identity. So it looks trivial. It is trivial. We want to get rid of it. But this is going to be isomorphic to the category of maximal Cohen-Macaulay modules of R mod delta.
Sorry, Colin, is F the same thing as delta?
F is delta, yes. Thank you. Yes. Thank you. Yeah, and so that's a theorem of Eisenbud. This is not so let me maybe write the words here. Maximal Cohen. Let me see. I guess we always write CM for Cohen-Macaulay. Right.
Question?
Yeah, please.
So you said it's a category for, is delta fixed in my category?
Yeah, delta is a fixed. We fix a particular delta, and we're looking at the matrix factorizations of that particular delta. Yeah.
Then how does direct sum work?
So over here, direct sum is just block direct sum.
But shouldn't that give me delta plus delta then?
No,
Delta plus delta is delta.
Yeah, because we'd have I think that's
all right.
Or ID. Oh, I should put a little ID in here and here.
Sure.
Yeah. So no, I think it's fine. Yeah.
Okay.
Or it should be fine. It's a theorem. It's a well-known theorem. So let's see. So and I was going to explain how this works a little bit. I mean, so the directions. So one direction is we have our pair of matrix factorizations. I guess I was writing B A. So we have a matrix factorization of delta, and we send that over to the maximal Cohen-Macaulay module, which is just the co-kernel of, I want to get the co-kernel of the first one, which is B here. Okay. And you can see, the co-kernel of 1 is going to go to 0, right? So it's pretty clear we want to kill that if we want this isomorphism. And then the other direction is also pretty simple. If we're given a module over here, so this would be a module in here, what do? Our module has a resolution, and since it's maximal Cohen-Macaulay module over a hypersurface, it's going to have a resolution R goes to B, goes to R, goes to M, so it's going to have projective dimension 1. So it's going to look like that, and then we'll have a matrix here, B. I guess we need some numbers here. Yeah, and so this will go to B, and then once we know one of the two matrices, we know the other one by the same sort of trick as I mentioned before, determinant B inverse. Okay, and so that's how we go from the matrix. So this there's more to do prove this, of course. It's a theorem. But one of the important things that Eisenbud noticed is that if you take any module over R mod delta, you start resolving it, eventually you get a 2 periodic resolution. And so you end up getting this AB repeatedly. Okay? And so that's something that's part of this proof, essentially. All right. So that's matrix factorizations. And I'm going to say but this is something I really don't know anything about, but they're important in well, I don't know, string theory, Landau, Ginsburg models. I mean, so the matrix, the category of matrix factorizations is the same as the maximal Cohen-Macaulay modules for hypersurface. And so it's important for things. Well, maybe I'll just write string theory. I won't say any more because I really don't know anything about this part of it, so I don't want to say too much. I'm sure I'll say this. So, but definitely matrix factorizations come up in this context a lot. All right. So my particular interest, I sort of realized after I wrote my title that like finding a matrix factorization of something is not super difficult. So what I really am more interested in is certain collections of them. And so here's a problem that's of interest to various people. So people like me who do kind of non-commutative geometry, whatever that is, and then there's the people who are interested in this kind of string theory or are also interested in the same problem. So given our polynomial, our delta, just arbitrary right now, delta is in some polynomial ring R. Find some modules or matrix factorization. So it doesn't really matter what we want because they're equivalent in. So this is to be some subset of MCM, maximal Cohen-Macaulay modules of R mod delta. So as we pointed out, this is equivalent to matrix factorizations mod 1 delta. Well, of delta. Let's put that in. Right. So find a set like this S. So the endomorphism ring of the direct sum of the MI, this endomorphism ring will be over R mod delta, has finite global dimension. Okay, so this question is of interest. This thing here we can define as a non-commutative resolution of the singularity of R mod delta, which will typically be singular. But there's even non-commutative resolutions of smooth things, and so this is a very, like, the existence of this kind of thing is very open. And there's lots of known cases, but it's definitely unknown if this can always be done, when it can be done, what the conditions are for it to exist, and how you find them. And so it's really, in some sense, this is sort of a commutative algebra problem in the sense you've got what are the conditions on some modules. They're already nice because they're maximal Cohen-Macaulay, but you want them to be even nicer for this non-commutative ring here to have finite global dimension. That's sort of an extra condition you're adding. All right, and so these are known to exist in a variety of circumstances, and I'm going to give an incomplete list of sort of references. So these are known in various special circumstances. I would say one of the older cases is finite MCM type. So this is like finite representation type. All your maximal Cohen-Macaulay modules are direct sums of like a finite number of generators. And this, whenever this holds, you have a non-commutative resolution. In this particular case we're talking about, where we have a hypersurface, this is equivalent to simple singularity in the case of a hypersurface. And these are classified by ADE. And in particular, they're the famous Duval. This is related to the Mackay correspondence in dimension 2, although it works in any dimension. Okay, so this so that's one case where these are known to exist. You just take all of them if there's a finite number. There's quotient singularity, so this is one case where it's known there exists an NCR. Another case is quotient singularities. Actually, maybe that's quotient. It says quotients by finite groups. Okay, and then there's a bunch of so these are kind of really classical. I mean, maybe I should mention Auslander, like when we mention names, I can mention Auslander here. Quotient singularities, it's sort of hard to attribute that one. I would say so for toric singularities, there's not really complete results. There's some open questions there. But I mean, there's some paper by like Faber Smith. There's Spanko Vandenberg. Okay. There's generic. There's known non-commutative resolutions for generic determinantal varieties. This is Bookwites, Lushka, Vandenberg. And then there's more, but I'm going to mention one in particular that I'm going to be referring to. So this is discriminants of reflection groups. So in particular, SN. And this is by Ragnar Bookwites, Faber, and myself. Okay, and so so basically when we know there's some kind of non-commutative resolution, usually it means there's some kind of extra structure we have. Okay, and these are of interest. I mean, not just for string theory, but also, I mean, for other situations, you want resolution serve as improvement of your variety, and these also give various kinds of improvements of your variety. Anyway, okay, so in particular, we found these non-commutative resolutions of discriminants of reflection groups, and I want to explain quickly how we did that, and then show how that's related to what I'm going to talk about today. Okay, so we were talking about the discriminant delta is x. Well, it's so delta is going to be, we're going to have Sn acting on say our roots mod we're going to mod out by the sum again. Okay, and then we're going to have the discriminant delta is going to be the product of the xi minus xj squared I smaller than j. Okay, so that's the same as we mentioned at the very beginning. That's where discriminant is. But furthermore, this is a square, right? So delta is, so if we just we'll just call this z squared here. Okay. Okay, so z is going to be the product xi minus xj without the squaring, right? All right, so now we're going to take this guy here. We called him S, and so we have S goes by Z to S goes by Z to S. Okay, and this is isomorphic to R. R is the fixed ring. Okay, R to the n factorial. Okay, so S is a free R module. It's R is a polynomial ring, and S has to be called Macaulay. It's a free R module, and its rank is the order of the group, which is n factorial here. Okay, so we have here this map here, p push forward. So I'm going to call it p push forward of z. I mean, that's a little kind of algebraic geometric notation. We have our map z on the variety up above, and I'm thinking of pushing it forward down to the variety down below. Okay. It doesn't do anything when we push forward like something by a finite map. It's just relabeling it, because p push. The point now is that this is a matrix factorization, right? So we know z squared is delta is in our ring R, and so p push forward z, p push forward z is a matrix factorization of delta. It's big. It's unfactorial sized matrix, but it's a matrix factorization of delta. Okay, and furthermore, it gives you one of these non-commutative resolutions. So the endomorphisms of over R mod delta of S mod Z, the co-kernel of Z, has finite global dimension. So it's a non-commutative resolution of delta. Okay, so this is the content of this paper by Bookweitz, Faber, and myself. Okay, so we know we have this non-commutative resolution, and it's given by this matrix factorization, or if you prefer, this Cohen-Macaulay module here, and it's huge. So we were able to tell pretty easily. So we want to know what is this matrix p push forward z, right? What is it? Okay, so you'd have to choose some basis here for Rn factorial of for S over R. So you need a basis of S over R to write a matrix, right? All right, so to write the matrix, and you can see we were able to show, like in the case of S3, we could get a matrix that looks like the following: delta 1 m m. So it's block anti-diagonal, where m is basically the thing I wrote down at the beginning, the matrix factorization I wrote down before. Okay, so this m is I mean, it was a little larger. That was because it splits, or because we're killing the p1. But anyway, so this is more or less the matrix factorization I wrote down at the beginning. Okay, so for S3 we have these are 1 by 1, and then we have these 2 by 2 blocks appearing. Okay, so what you have to do to do this is find a basis where you can get this kind of nicer description. And the point now is that you have p push forward z splitting into smaller things. Okay, so p push forward or this matrix factorization splits. Okay, so we have this giant sort of matrix, and we want to make it smaller. And partly we want to understand what the modules are that are making up the non-commutative resolution. Why are they special? Well, what makes them make up a non-commutative resolution? Of course, having them all stuck together in a big direct sum is not helping us look at them. Okay, so for the case of S4, we were able to do this as well in the paper with Bookweitz and Faber, and we got something that looked like this. And we had, maybe I'll write B, so A, C, C, B, B, B. And so we ended up getting C, C twice, A, B 3 times, and B, A 3 times. So the sum of this and sum of this. And then the one in the delta, I guess one of them, the one in the delta. Yeah, you'd either need that once, but if you, or well, okay, I'll write down 2. I mean, one of these we kill, right, when we go to the, basically this is what the kind of decomposition we got of this. All right, and so you'll probably see, the representation of S4 S4 coming up here, and that's not a surprise. And so what I want to do now is explain. So this took me, basically, I did a lot of computation to find this decomposition, and we have, A, B, and C explicitly computed, and this took a lot of work. And so what I wanted to do is to do this for higher degrees. And so I asked an undergrad to work on it. And so he worked on this, and he did. Oh, and I supposed to mention this at the beginning. So this is joint work with Faber, May, and Tallarico. Yeah. So yeah, sorry, I should have mentioned that right from the beginning. So Tallarico, Marco, I asked him if he could try to compute this, for S5 and so on. And so he spent a lot of time trying to look for different bases. There's a push forward package in Macaulay 2. He had kind of rewrite because he had to choose the basis himself, not have it chosen for him with some Grosvenor basis method. So he was looking, he tried lots of different bases to try to get lots of zeros. He was making some kind of progress, but then the real breakthrough came when the existence of what's called higher spect polynomials was found by us. I mean, so maybe this is something I imagine people in this audience already knew about these things, but we were looking for some kind of basis for S over R that respects the representation theory structure, and this is the thing we're looking for. All right, so we know S is isomorphic to R tensor the covariant algebra as a representation, right? So if this is the covariant algebra. It's also, and the covariant algebra is a regular representation. So this is KSN as oops, should be down here as SN representations. Okay, so forgetting the other structure, just remembering the SN representation structure. These are two statements, right? Okay. So it's our tensor, the regular representation. So we also know these are isomorphic to our tensor. So this is direct. We know that lambda partitions of n index the representations. So this would be, say, V, the irreducible representation corresponding to lambda, to the dimension of V lambda that occurs dimension many times, right? And so what the higher spect polynomials do is they give us a basis which realizes this. So we get a decomposition over the irreducible representations, but furthermore, a decompositions of over pairs of standard tableau of but I'll just put that's my base field K here of FVT. Okay, so I have to introduce a little bit of notation here. So ST lambda is going to be set of all tableau shape lambda, standard tableau of shape lambda. Right, so we're summing over pairs, right? So we need pair many because that's V squared, right? Dimension V squared many, right? So we need pair many standard tableaus. And the FVT are what are called, these are in S. Okay, so this decomposition is happening inside S. These are explicit polynomials. These are in S, and these are called the higher spect polynomials. They're the things that carry this out. All right. So, and these are due to Ariki, Terasoma, and Yamada. All right. So And so these look like we found these and we thought they'd be the right basis to use, and they're not quite. So we need the FVTs, the higher spec polynomials, and a variant. So a modification. Okay, they're not really super different, but it's a sort of simple modification. All right. So let's let T be in so a standard tableau of lambda, where lambda is a partition of n. Okay. Then C of T is the column stabilizer. Okay, so it's a group that stabilizes the columns. It's a subgroup of Sn, and R of T is the group stabilizes the rows. Okay, it's a subgroup of Sn. And then CT is defined to be the sum of the sine of C times C over the column stabilizer, and we have RT similar is the sum of the R without the sign modification of R in RT. Okay, and then the epsilon T is CTRT, and this is the Young symmetrizer. It's a standard thing, which I'm sure lots of people here know. And then we have sigma T is the variant that we want. This is going to be RTCT. Okay, so you see it's a sort of a slight modification of the original one. Okay, and so these are these sort of idempotent up to scalars, and they give a projection onto the V lambda, so the irreducible representations indexed by lambda. Okay, so the next thing we need is the charge. And so we have a charge. The charge of, and so in the interest of time, I think I'm just going to write down the charge. It's a, yeah, I'm just, yeah, I don't really know what people know and don't know about these things. So I'm just going to say the charge. It's a vector of length n. Okay, and we're going to have a monomial xvt is going to equal x to the word of the tableau sub I of the tableau, which by definition is the product of over j of x. So x, the variable given by the charge sub j, and then the word of t sub j. The word of t of j is just sort of walking across the tableau and recording that vector or from bottom up. Okay, and so the higher spec polynomials are these f vt is epsilon t xtv, and hvt is sigma t xtv. So the only difference here is that we're using a different idempotent, and this is the sort of variant of the higher spec polynomials. All right, so they need to be ordered, and we're going to use a lexicographical and least letter ordering. And so to save time here, I'm just going to show you. Can you see that there on the screen? So this is the ordering we're going to use to order. So for S4, this is a total order of all of the standard tableau. Okay. And you can see here the monomials and so here's a computation of all of the spec polynomials here. Okay, this example here. So I'm just going to flash that and then take it off and keep writing here. So we ordered using least letter, least least letter ordering. Okay, so it's a linear order of all the tableau and all the partitions and all the tableau. And now the point now is that we get the following theorem, which is the matrix factorization decomposes as a direct sum, as we would hope, as lambda partition of n. T is a standard tableau of lambda of the restriction of these to h t dot comma. So we have two bases, and we're going to change bases different. We're not going to, we're allowed in our matrix to change bases on the left and the right differently, and that's what's happening here. So we're using the space spanned by the HTs, where we let the top variable change, or the FTs, where we let the top tableau change. Okay, and furthermore, we get this AAA pattern, right? So there, we have so if we take p push forward z restricted to ht1, so we get a repeated matrix, right? Like a dimension many times, t1, t2, or shape lambda. So we get the same thing here with a 2 in it. All right. And then the last thing I want to say is using pairing. And then this idea, well, I mean, Francois Bergeron, I'm talking to him, he told me these pairings are very useful. I don't know if this is similar to the ones he was suggesting, but we have a pairing going from S. It's an R linear pairing given by FG is the sum of this sort of alternating idempotent. So this is always alternating. So we can divide it by the Z. It's always going to have Z as a factor because all the alternating things in S are given by that. So we get, oh, sorry, it's R. It gives us a polynomial R here, in R here. And using this pairing, so using this pairing, we get Fi Fj has a form like this. Okay, so it's sort of lower or diagonal, well, it's a triangular, anti-triangular. Okay, and that's enough to get a formula. And I'll show you the formula in a second here. And I just want to, one last thing I want to mention is in progress, we're working, so Simon May in particular, so Simon Mays, he's a PhD student who's finishing soon, looking for a postdoc. Marco's an undergrad who's finishing soon. He's looking to do a master's somewhere. So Simon May, that's Eleonore's student. He's been doing a lot of work on, we're all working on this together, the GN1M, which is the SN wreath mu, the diagonal mu m's. And so that's another big case of reflection group. So we want to understand in a similar way. And that is everything I wanted to say. I'm going to quickly just show you the formula. So using this pairing, you can get the formula, which is down this thing here, is the formula. So it uses explicitly this pairing. It's a standard, it's, well, not, it's a modification of the standard kind of thing you would do when you have a pairing to extract the coefficients, right? And then here's the matrices for S4. The Fs are the invariance polynomials. So these are the sort of interesting matrices for S4. And for S5, it gets really big. So I tried to fit it on a page and I had to turn it sideways and shrink it. So anyway, there it is for what it's worth. Anyway, that's it. Thank you for your attention. Oh, and I'd like to thank all the organizers. sorry, we do questions first, and then I thank the organizers. I got that out of order.
Thank you. That was a really nice talk. Let me ask, are there any questions?
Sorry, can you repeat the definition of this charge again?
Yeah, so I was, to finish on time, I didn't actually define it. But since you asked, I can take the time to define it. Yeah, it's the exponent used on the, as you said, or Nantel said, it's the exponent used on the, yeah, since you asked, I can quickly define the charge here. So I'll go back to where I was going to do that. So we have, so I mean, I was going to do it in terms of an example because it's easier for me to remember how that works than the actual definition. Okay, so then we have a word of t, which we start here and read up. So we get 6, 3, 1, 5, 2, 4. So that's the word of t. So it's a permutation just by reading, sort of starting here. And then the charge of t. So we start at position 1 and we get a 0. And then we go to position 2. And if it's to the right, we get a 0. We don't increase. And then we go to position 3 because it's to the left, we increase. And position 4 is over here, so that's fine. We don't increase. And then for 5, we have to increase because we're going back. And then 6, we increase. So that's the definition of the charge. And I imagine that's the kind of thing people are very used to in this kind of setting. And maybe
I've never seen it in this setting.
Okay, yeah, I mean, I know it's the kind of things that comes up a lot in combinatorics that I don't know a lot about. But it's used sort of as the, I mean, if you remember, there was the FVT was sort of X, this epsilon, where you use the charge. The charge is basically the exponent as a vector, right? So those are both vectors. So it's a multi-index there.
Oh, is this to get those second factors of the same dimension? I mean, of the same reducible type?
Yeah, I mean, so one of these, sorry, I'm not sure. I mean, like we have two things here, right? And so one of them is moving across a particular representation. That would be this, and then this is changing which copy of the representation we're in. I'm not sure if that answers your question.
So there is probably one T for which the charge is just 0, right? For each partition, at least.
Well, no, I mean V and
Not
T
0 there. It has to be at least
the same shape. They have to be the same shape.
The minimal charge is when you put all 0 at the bottom and then 1 in the first row and 2, so it's n of t.
The degrees of the charges are going to give the degrees of where the representation shows up.
Oh yeah, the degree, yeah, definitely. The degree of the charge tells you which degree that the representations appear. Yeah, I mean, this is an example here where I have these monomials. These are the including the charge and the weight vector. I don't have the detail in here of how they're computed though. This is.
Well, thank you.
Thanks.
Are there other questions? If not, let's thank the speaker again.
Okay, now I jumped the gun earlier, but it's my chance to thank all the organizers for a very successful online conference. So I was very happy to attend. I learned lots of new things, and I guess maybe the next one will be in person. Maybe we'll see. Maybe a combination. I guess we'll find out. Okay, thank you.
Yeah, I also want to thank the other organizers who presented the other days, Jenna and Nancy Wall, Jenna Rudgegoat and Nancy Wallace and Nathan Grieve. They worked very hard on this. It's not a lot to organize one of these, and we are recruiting for volunteers. So if you're interested in being an organizer next year, we need 3 or 4 people to do a little of the work. It's just a little time each month to make sure that things are on schedule. But if you're willing to either get in contact with me or one of the other organizers, or we can put you in touch with the next organization. So we're working on it. I don't want to announce anything formally until after we speak to the potential next organizer.
So next year will be the 20th edition.
Yeah. It'll be a big one because it will also be in person, first time in 3 years. Hopefully. That's what we thought this year. And Fields told us that no, you can't go in person. And we didn't believe them. And it turned out they were right. Well, thank you. So I just want to say closing. Hopefully see you next year.
Thanks, everyone.
Let's just say let's unmute everyone and a big round of applause for the organizers this year. On the count of see you all next year, hopefully in person.
Mike, you should stop the recording.
Oh, thanks.